looking at topic models. I briefly described that. There's a whole range of models that can be recovered using this method of moments, and that got me into thinking maybe we should go deeper into probabilistic graphical models. I had briefly introduced the notion of conditional independence through the graph, and we had this graphical description, but today we will go deeper into that. I think the original plan was non-convex optimization, but we covered a lot of it as we did tensors, right? We talked about saddle points, we talked about stable points. So I think, given that was covered, I feel like the big gap is probabilistic models, so it's good to have that grounding today. And then next class we can do competitive optimization. Okay, so how many of you have done a course that involved graphical models? Yeah, not a lot, so it's good. Okay, so that was a good. I think I had briefly described in the previous classes, but let's look at the different definitions of what a graphical model is, right? How do we use the graph to represent distributions, and what are the different equivalent notions? So when I talk about graphical models, we'll mostly deal with undirected graphical models. At a later point, I'll make a comment on the directed ones, right? So in this case, there is a graph that is undirected, right? That has vertices and edges, and I'm describing my joint distribution over a set of variables using this graph, right? So the nodes in the graph represent the variables. Nodes or vertices in the graph, right? And the edges represent dependencies. So the idea is, in many cases, right, it's not just some arbitrary joint distribution between the variables. There's more structure, right? There's the dependencies can be structured as a graph, and that's what we want to use this notion of graphical model to describe. And so the property with which we describe this, we call it the Markov property. So that's why an alternate name for this is Markov random fields. Because what this graph represents are conditional independence relationships or Markov relationships, right? The simplest one is, of course, the Markov chain, right? So if you have a chain of random variables, if you recall the Markov chain, right? So we have conditional independence, right, of the past and the future given the present. Right, so that's one way to kind of say that, right? So at any time t, given t minus 1 measurement, it's completely independent from the past, right? So, and we did introduce the conditional independence notation in the previous class. So if my variable is y, so yt is conditionally independent of, say, I'll write it as minus of t minus 1, so everything before t minus 1 given yt minus 1. So, right, so it's everything here, it's conditionally independent. Right, so that's the basic right example where the graph is simply a chain. Right, so if you want the definition, more generally, we have what is called as, we'll also call it the local Markov property, because we can describe the graphical model in multiple ways. But the most common one is, I have, let's say, a random variable as a certain node, right? It's, if I condition on the neighbors of the node, So I'll use n of I to denote the neighbors of the node. It's conditionally independent of everything else. So when I say minus, it is all the other nodes other than the neighbors. Right, so this is called.
Is the general the graph is directed? I mean,
it's undirected, right? So we look at undirected graphs. So that's what I mentioned.
This side and this side, for example, for the Markov.
Yeah, that's why I didn't put the direction, right? I'll come in a minute. I mean, the Markov chain has something, right, more in general, like, I mean, especially if you look at like an autoregressive process, right? It cannot be completely described by just the undirected graph, but we'll come to that aspect in a minute. So generally here, what I want is to describe, right, the dependence of a node and other nodes in the graph, right? If I condition on the neighbors, I don't have any more dependence, and that's the idea. So I have a node, I have its neighbors, right? And now there is rest of the graph, right? So now if I condition on these, right, neighbors of the graph, sorry, I'm then making it conditionally independent from the rest, right? So from all the other variables. And in the Markov chain, that was simply, right, here the neighbors are both the previous measurement and the future measurement, right? So if I do that, then it's conditionally independent of everything else. Here I only talked about the past. I mean, this way I can, cut this part of the chain, right? If I also condition on future, I cut the dependence on the other future measurements. Okay, so that's the notion, right? So once I tell you what are the values of the neighbors, I have no other dependence on the rest of the graph. Right, so if I have a large number of variables, but if the graph is sparse, so the idea is, right, I can control my dependency only through these neighbors. So, and the way to think about conditioning is the same as, right, kind of essentially erasing this node, right? So conditioning is like node erasure. And if I don't have any other edges left, right, that means there is conditional independence, right? So in this example here, I condition on yt minus 1, I erase this node, right? This node goes away. And so there are no more edges between this part of the graph and this part, right? And that's why they're conditionally independent. So you can visualize this conditional independence, right? Whichever variables I'm conditioning on, I can just erase them from the graph. And now I can check if there are still links, right? Whatever links are remaining, the dependencies are there. But whenever links are erased, you can look at conditional independence. Is that clear? Right, so this is in terms of the local Markov property. But there are also alternate definitions of Markov chain. The other one is known as pairwise Markov property. So here, now I'm talking about whether two variables yi and yj are conditionally dependent. And the property says that if they're conditionally independent given everything else, so I just take all the other variables other than I and j, right? And I condition on it, these two variables become conditionally independent. What does that tell me about the graph? If I use the first definition, right, what would that tell? Or if I use this property of node erasure, what does this tell me about the edge? Is there an edge ij? There cannot be, right? Because then that would not be true. right? So I can define my graphical model by looking at pairs of variables, and I want to check that as long as I condition on the rest, right? If they are not neighbors, there should be no dependence, because there would have been neighbors, right, in this set, and that would have made them conditionally independent, right? And then there is a third version of this, which is called the global property, global Markov. And what we just do is, what we wrote here for pairs, we'll just make it general in terms of sets. So YA is the set of random variables, right? So I take a bunch of nodes, right? I put them into set A. I look at all the variables in that set. And I look at how, whether that is conditionally independent with set B given set C. And this should hold for all A, B, and C such that C separates A and B. So we know the definition of separation of sets, right? So here now, let's say I have this graph connections, right? I have, let's say, here some nodes here, then you go to the other side of the graph, right? So here this is set A, set B, set C. So if I remove all the edges in set C, right, these two parts have no connections. Okay, those are called separators, right, in graph terminology. Okay, so separation implies conditional independence. And as you can see, this is the most general, right? So I want this to hold for all sets here. And so if I have this, then these two are implied, right? But the other way is not necessarily true, right, always. But they end up being true when there is what is known as a positivity condition. Right, so what the positivity condition tells you is that if the marginal is non-zero at a certain value, right, the joint should also be non-zero. So meaning you don't rule out any configuration, right? So let's first, let's think about only for discrete. You can also have a version for continuous, but discrete it's easy, right? So all the variables are discrete. You have a probability of taking any of the values, right? So we'll use pi of yi is, right, the values that yi takes, right? So let's say it has a certain set of values where it's non-zero, right? That should imply that any joint distribution, right, so pi of y1, let's say if there are n random variables, is also non-zero. It's strictly positive. For instance, let's say all the variables are just binary variables, right? So at each node, I just have a binary variable, and at each node, the marginal probability of taking either of the values is strictly positive. In that case, I want to make sure that all possible configurations also have non-zero probability, right? I don't rule out any configurations. So that rules out any deterministic relationships between the variables, right? So if one variable is a deterministic function of the other, this can be violated, right? So this is to ensure that there's always some other additional randomness in each variable you have. right? For instance, a trivial case is if two random variables are exact copies of each other. This is not true, right? Because then all configurations are not allowed, right? So what this kind of tells you is if there is enough randomness, right, across all the variables, then all these properties are equivalent. Otherwise, there may be a violation. And it's kind of intuitive, right? So if you have some form of like deterministic relationships, the graph is not enough to specify all the dependencies, right? So there's something additional there that just cannot be captured by the graph. And that's why if you rule that out, then you kind of have this completeness where I can have just a local Markov property and that implies the global Markov property. Right? As we said, the other way is true, right? If I told you there is a set of variables that satisfy the global Markov property, I'm done, right? Because it's for all sets. So then 1 and 2 are also true. The question is, if I tell you that only 1 is true, does that also imply 3? For that, we would need the positivity condition. Is that clear? So this is the notion of graphical model, right? So I'm thinking of it in terms of conditional independence relationships.
This was for discrete, I can see that this is available for continuity, when we have continuous and where this is hard to get something like this.
Yeah, so I mean there you can talk about it you cannot essentially describe a graphical model for any arbitrary continuous distribution, right? So that's where, when we have kernels, you can again describe a kernel to specify, pairs and marginals and have a way to do it. So most of the graphical models deals with discrete because it's hard to define dependencies over arbitrary continuous random variables. On the other hand, if it's something, let's say Gaussian, for instance, or a parametric set of distributions, you can still have these kind of similar specifications. But it's hard to do it for arbitrary continuous distributions. And that's why it's mostly completely developed for discrete, right? So there is some theory for continuous, and most of it is only for Gaussian, right? Beyond that, it's very hard to come up with very general properties like this for continuous distributions. That's a good point. Okay? So far, right, we've only talked about graph specifying these conditional independence relationships. An actual question is, what does my joint distribution look like, right? So does my joint distribution factorize, right? And if it factorizes, how does it factorize with respect to this graph, right? So we can again go back to the Markov chain example, right? So if I have this Markov chain here, right? So if you recall, if I want to specify the Markov chain, we did this in the previous class, right? We had the initial distribution, and all I needed was just the transition matrix, right? So we had T as the transition, which is nothing but how does the next state evolve as condition on the previous state. And this way we could specify the entire joint distribution, right? So if I had like now y1 through say yn, I could like start with p of y1, right? P of y2 given y1, p of y3 given y2, and so on, right? So these were the transition matrices. In the case of when it was homogeneous, it would even be exactly the same matrix, right? And that's why we could like kind of come up with ways to learn that, right? In fact, we were going beyond Markov chains to hidden Markov chains in that class. And so what this tells us is this joint distribution, I can factorize it, right, along the graph here. In this case, it's simply a chain, so all I need is these pairwise, right, and then, pairwise functions. In this case, it's the conditional distribution and marginal. In this case, the only marginal that's needed is the first node, right, the starting condition. So the question is, more broadly, is this true on any graph? Right, so can we factorize the distribution based on the graph we have? Is the question clear? On the Markov chain, we see the joint distribution factorize in terms of, right, the initial distribution and the transitions, right, and the transition is just the conditional distribution of the next state given the current state. And it turns out, yes, it is the case. You can do it for general graphs too, but it's not as, of course, simple as the Markov chain. And this is called the Hammersley-Clifford theorem. And so in the very general case, what it says is the distribution has a Gibbs form. So we'll, in a minute, it's also related to, right, in statistical physics where we talked about Gibbs distribution. And what that says is if I now have, right, the joint distribution on a set of random variables, so let's say there are n random variables, it is proportional to a factorized form, right? So, and this factorized form consists of functions that involve cliques in the graph, right? So this, because right now I'm making I've not made any assumptions on the underlying distribution, right? The only assumption I've made is, right, it has this positivity condition, right, and it satisfies this Markov property. Anyway, under positivity, all these conditions are equivalent. So if I make this assumption, right, what it says is I have a function that involves groups of variables, right, and each group is made up of the cliques in the graph. And you could also have functions that are specific to each clique. So I guess the question is, what is a clique? Just to recall, clique is a complete subgraph, right? So if I have, for instance, in this case, right, so I have this edge as a clique, right? So, but then here the triangle is a clique, right? So I can break down my distribution, right, into these edges and this triangle here. So I can factorize it into those parts. So what this says is the joint distribution should have this factorization form. So when we did our classes on statistical inference, right, we talked about sufficient statistic. And if you recall, even there, we talked about factorization forms, right? In that case, it was the Nyman-Fisher factorization. And there, the question was, what are the parts that are relevant and what are not, right? So here, it's a somewhat different context, but it kind of, again, goes to the same kind of ideas, right? Can I simplify my distribution in some factorizable form? Okay, and if I promise you these Markov properties with positivity condition, I can guarantee that you can always factorize the distribution. And this is very general, right? Of course, there are trivial cases, right? So if the graph has no edges, what would be that distribution? What would that be? If there are no edges, just independent, right? So in that case, it's just, the factors are trivially just the marginal distributions of all the variables, right? If it's a complete graph, that's just any arbitrary distribution, right? So if it's complete, this entire clique is just the full graph, right? So there is no factorization. But you can have all kinds of things in between. Right, and in this case, what we saw with Markov chain, right, these factors here correspond to the marginal distribution and the conditional distribution, right? So I can have here, right, more properties than the general case, right? Because I'm relating these functions phi to also the marginal distributions here, right? So I'll write down one more form here which will be useful. So I can rewrite this in terms of the joint, right, between the pairs. Right, I can have this. And so I can kind of do like in terms of like chain, right? So if I just like move around the factors, what this is made up of is the marginals at each node and joint between pairs of nodes, pairs of neighbors, right? So we'll also have that special form in the more general case whenever the graph is acyclic. So if G is acyclic, chain is a special case of acyclic graph, right? Tree is an acyclic graph, right? More generally, acyclic could have forests, right? So meaning tree means all the nodes are connected, but if you don't have edges that are present everywhere, those could be forests, right? So those are acyclic graphs, right? So meaning there are no cycles, right? So you cannot complete the loop in G. So if that's the case, you even have further, simplification, right? Because here, the challenge is these phi, right? So these function phi, we'll call them potentials. Like how do I relate phi to marginal distributions of this set of random variables? It's not clear. Right? It's not easy to directly relate because the challenging thing is there is the normalization here, right? So we need to normalize. On the other hand, if it's acyclic, I can directly write down in a special form where this is made up of product of all the marginals on the nodes, right, and also product of pairwise marginals on the edges. Right, this is much nicer because I can easily compute, if let's say I have a whole bunch of data, I can easily collect empirical statistics of my pairs and marginals, right? So with even a small amount of samples, right, this can concentrate. But if I try to directly compute empirical distribution of my joint, if there's a large number of variables, that would take exponentially more samples to concentrate, right, for a general distribution. But by having this form, what this says is all I need is marginals of nodes and pairs. I mean, of course, if I have marginal of pairs, I can also get marginals of nodes. Right? So all I need is marginals of pairs over the edges of my graph. Right? That's sufficient to specify the joint distribution. And so that there we talk about efficiency of now estimation. Right, because this joint distribution is so simple, I can now learn this from data much more efficiently compared to an arbitrary joint distribution.
I understand that if you have this graph, then for your inference, you're doing this. But before we start our problem, for example, we assume that there are a bunch of random variables, we observe something. How we can understand the graph? How we can know that this is the right graph?
So then we are talking about learning the graph itself, right? So I'll come to that in a minute. So so there are so many parts about learning here, right? So sometimes maybe you have domain knowledge, you make an assumption that it is a graphical model, right? For instance, Markov chains, there may be many structural properties where you know this is Markov chain, right? Or you make that as a simplifying assumption. And there you know the ordering. If you know like measurements are arriving in order, you make a simplification, this is Markov chain, right? So there you fix the graph. But in many other cases, you may not know the graph and you want to learn from data, right? So that's what we call structure estimation, estimating what the graph is. And once I estimate the graph, the next question is, how do I estimate the joint distribution? And that's where, if it's acyclic, you have much nicer properties, right? Because once I know the graph, once I know my marginals along the edges of the graph, I'm done, right? I tell you what's the estimate of my joint distribution. On the other hand, if it's a general graph, right, with cycles, it gets hard.
Even in this one, what if, for example, the data, the distribution is somehow that empirical data, that one really goes are you really going to compute that because of your assumption that you have that? Because it is possible that in empirical this I don't observe that much sum. So the probability is going to be zero.
No, you're assuming it has this factorized form, right? And what this tells me is I don't have to try to compute my joint distribution. All I need is to compute the marginals. And sometimes maybe it's also hard to observe the entire joint distribution, right? There's missing data in many practical applications. But maybe you have much more amount of data between pairs, right? So even then, this becomes efficient. Right, because in practice, right, so let's say these are, say, binary variables, right? If each state is binary and there are n variables, there are 2 to the n number of configurations, right? So if I have a general probability distribution, I need exponentially many number of samples for it to get any error bound where it grows with n, right? So it's exponential in n. And that's where these graphical models can be helpful because they simplify the complexity of the distribution. Okay, so and here that's what is hiding, right? So with the acyclic graph, this is great, right? So I have complete tractability. But then if it's a general graph with cycles, right, the challenge is I still need to do the normalization. So usually we call the normalization constant to be z. So what I have is p of yn is this, this factorized form. But then there is this normalization. I mean, in low dimensions, this is trivial, right? All I need to do is just sum up over all the configurations. But then, if I have a large n, what is the challenge? I have to sum up over 2 to the n possibilities, right? This is sharply hard, right? So that's why, right, that's where the elephant in the room is. I cannot evaluate my distribution even if I have a nice factorized form. And that's why going from acyclic to having cycles makes it, right, exponentially harder. Because in a general graph, I cannot easily relate these potentials to marginals. Okay? Right, so if it's discrete, then I have 2 to the n possibilities, so in general, that's sharply hard. Right, so I'll briefly look at now Gaussian distribution where things are much nicer. Right, so I'll do this because it's kind of very quick to see what is the relationship between, right, my covariance matrix. Right, so let's just do zero mean Gaussian because the mean really doesn't affect the graph. Right, so here I have the covariance matrix. I can completely specify my joint distribution using my covariance matrix. Right, so that's all I need for Gaussian. So the question is, how does this relate to if there are any Markov properties? Right, so if I have Gaussian, I know my distribution, right, is related to this. I'll just make it, as I said, make it zero mean. Right, so this is my joint distribution for Gaussian, right? And I do even know the normalization there. That's just the determinant, right? So that I can compute in cubic time, so it's polynomial time. So everything is completely specified, but how can I relate this formulation with Hammersley-Clifford theorem? I think you can see that almost quickly, right? Right, because if I can just rewrite sigma inverse, I'll call this another matrix A. Right, so this exponential form, I can rewrite it in terms of course, there are the self terms. All I'm doing is expanding this quadratic form. Right, so in this case, xy square plus right, all I did is expand the quadratic form. Right, so what does the Hammersley-Clifford theorem tell me? If I, in addition, told you it's Gaussian and there is a graph that gives me the Markov property, what is the simplification I have? In an arbitrary Gaussian distribution, I have this ij over all the pairs, right? But if it's if I tell you there is a specific graph that gives me the Markov property, what is the simplification I obtain?
I and j have to be neighbors.
Exactly, right? Because the Hammersley-Clifford theorem tells me that only the cliques in the graph matter. Right, but the Gaussianity tells me I only need to look at pairs, right? I don't have higher order potentials. So, and the only cliques that are pairs are all the edges, right? So that's why I have this. So that's the other simplification. So we call this the potential matrix, right? So here these were potential functions. In case of Gaussian, this is called potential matrix. And what the potential matrix gives me is the graph, right? So whenever there are non-zeros in the potential matrix in the off diagonals, only those are neighbors, right? And there are no edges whenever there is zero, right? So meaning aij is 0, right, is equivalent to saying there is no edge in the graph. Do you have a question? Yeah. Right, so in addition to Gaussianity, I can further exploit Markov property to make my potential matrix sparse. Right, so that's one of conditional independence, right? On the other hand, if I had, let's say, my covariance matrix had 0 entries, right? I mean, we are all talking about zero mean here, right? So this is all, the whole thing is zero mean. Otherwise, you'd have to mean correct each of them. So if this is 0, right, that means I and j are uncorrelated, which is different from entries in the inverse being 0, right? In that case, they satisfy the conditional independence or Markov property. So these are not equivalent. Right, because this is uncorrelated, right? Because all I have is xi, xj is 0. Whereas if I have it in the inverse, that has to be all of these Markov properties. And in case of pairs, that would be this property, right? So if there is no edge here, the conditional covariance would be 0, right? Between I and j condition on everything else. That's what that would imply. Right, so if this is 0, this is equivalent to saying, right, conditional covariance of this given everything else, right? This is 0. So that's the difference. Any questions here? Okay, so in general, right, so even for discrete, I can end up with all kinds of cliques in my graph, right? So, but there's a special class people study a lot, so I'll just quickly mention that. This is called the Ising model, and that's kind of the counterpart to discrete, right, of these kind of pairwise models. So in this case, my, right, clique potentials, right, that I had here, right, so that's only like, I just have my pairwise potentials. And these are just, in this case, just product. And sometimes there is like a, scaling factor, usually that's j. And it's 0 for all higher order cliques, right? So I only look at pairs in my factorization form, and I set all the higher order terms to be 0. That's called the pairwise Ising model. Usually Ising is always pairs, but sometimes you also emphasize it's pairwise. So you can make simplifications like this, right? So I can say, yes, if I don't tell you anything more about the distribution, you could have all the higher order cliques, but I will simplify it and only look at, right, interactions between pairs. And this is the model for like magnetism, right? So, and for states of matter. So you can have like, right, like ice, liquid, and gas, right? So those are different states, and how the correlation is in these different states. You're like looking at the right global effects. So what is the strength of local correlations, and what does it lead to global correlations? And that's where this is studied a lot in statistical physics, and hence the term Gibbs, right? So if you've done a course on statistical physics, you would have, looked at forms of this, and you would have looked at Ising model, right? So that's why there's a lot of connection between the two fields, right? And here you're talking about the energy of the states in statistical physics. Okay, so I won't say more, but just kind of, right, the main connection that's really interesting and deep is what are the phase transitions and correlations in a large-scale model, right? So in the standard 2D Ising model, for instance, what I have is this kind of lattice, right? So I have like this 2D grid, and I have connections only along the grid, right? So that's the graph, and I usually assume this to be homogeneous, right? So this term J is like the inverse of temperature, right? And that's the physical kind of intuition. Like if I have a large temperature, my J is small, right? That means the interaction is weak. and that is the gaseous state, right? So if it's a gas, there isn't a lot of interaction between the molecules, right? It's very weak. Whereas if it's ice, right, the interaction is strong, that means the J is large, right? Then the temperature is small. And so that's where these physical models are used. And the phase transition means I go from one state to another, right? So I go from ice to liquid. That means in that transition, right, the correlations break down. Earlier there were strong interactions that kept it as a solid. And then when I increased the temperature, it broke down. And so this is also known as correlation decay properties. And the main idea is, right, so I can take this lattice to be infinitely large, and I can ask, what is the correlation between the node at the origin and at infinity, right? Is there finite correlation, or is it kind of decaying, right? It goes off to zero. And in the gaseous state, it just goes off to zero, right? There is no correlation between a molecule, let's say at infinity, and a molecule at the origin. But if it is in the state of ice, there is some finite correlation, right? And that's what keeps the structures together. And so all these fundamental properties of materials, right, can be studied by looking at these Gibbsian models, right, these Gibbs forms, and looking at what are the correlation properties in different regimes of temperature. Okay. And as you can see here, there are cycles. I cannot just directly write down this distribution. And that's why there are all these large-scale simulations, right? So how do I simulate this at scale? What kind of approximations do I make? I mean, that's why it is, right? More than a century-old line of study, because it's highly non-trivial. And things get extremely hard going from 2D to 3D, right? Even just in 3 dimensions, so much is still an open question in giving precisely what are the nature of phase transitions. Okay, so if you do statistical physics or a course there, you would go more into depth. But I think the connections are very interesting because you can ask this same kind of questions also to machine learning problems. One of the things I had worked on a while ago was precisely that question on how phase transitions can tell me which problems are easy to learn, which problems are hard, right? The intuition is, if it is more in the gaseous state of matter, right? So similar to the gaseous state, in water, I could think of gaseous state for various distributions, right? Meaning the correlations are weak. In that case, you can locally estimate distributions even when it is not acyclic, and you can get away, right? You get a good approximation. But on the other hand, if it's in the solid state, if there are strong correlations, you cannot just locally estimate and ignore other parts of the graph, right? Because there is that correlation transfer, right? So algorithms become much harder. I mean, to get any good approximation guarantees is hard in that regime, right? So you can talk about when problems get easy to learn and when they get hard, depending on these phase transitions. And of course, right, this is also a modeling question. Is your data, do you expect lots of correlations in your data, or they're weak correlations, right? That can also tell you what kind of approximations to make while trying to estimate these graphical models. Any questions here?
Do you use the critical exponents to look at these phase transitions?
Right, so the critical exponents are essentially where the phase transition happens, right? So what is the temperature where these phase transition happen? And that's where, right, in many cases you may not be able to exactly compute this because that itself is hard, but you can make various approximations. You can have bounds on what these should be. And you can also try to estimate that from data. So it's an interesting question of also testing. What is the phase is your data in, right? And what algorithm to use, right? So, with deep learning, you've heard a lot about AutoML and hyperparameter optimization, right? Like right now, it's mostly trial and error. But what these kind of phase transitions give you is a much more principled approach, right? If you could approximate these exponents well, that guarantees, right, telling you which phase is your data in and hence which approximations are good. But that's an open problem on how to do that. But that's where I think it'll be very interesting to look at this further. So how many of you have seen this kind of Gibbs state, taken course in statistical physics? Okay, yeah, I guess, right, that makes sense. I guess more from the neuroscience background, you'd have this. But I think there are lots of interesting connections here. Any further questions? Okay, so that was a quick kind of, right, overview of statistical physics. The other aspect that's also somewhat tangential, but I want to make a comment is, this graph does not tell you everything about the distribution, right? That's what we already saw, because in general it is made up of these cliques, right? Potentials over cliques. But if I have additional information, for instance, it's Gaussian, then it's only pairs, right? So I can get all kinds of simplifications if I tell you more about the distribution. Right, so this Markov property does not specify a distribution completely. And one of the things we said, right, for instance, if it's a Markov chain, we also know causality, right? So it is evolving forward in time. And that just the graph does not tell me, because the graph is undirected, right? So we'll kind of quickly make a comment on that and causality, and I'll tell you what the difference is. So, in this Markov chain, I can explicitly talk about the next state as a function of the previous state, right? So that's my autoregressive model. So I have, like, say, yt is some a yt minus 1. So let's say these are vectors, right? Plus some noise, right? Usually some Gaussian noise. Right, this is my standard autoregressive model. Right, so the next state is a function of the current state, right, some linear transformation and noise. Right, so if it's just the undirected graph, right, that's not always equivalent to this model, right, because this is going forward in time, whereas here there are no directions, right, so, and that's the difference. So this equation isn't completely specified by this graph. But of course, once I have this equation, I can also get my undirected graph, right? So it goes in this direction, right, and not the other way. So the question is, this causality property, are there other ways to test for this? So it's clear if I only did test for conditional independence relationships, right? Because when I collect data, I can compute my empirical distributions, I can do a conditional independence test. Right, but that is not enough for me to infer this equation, right? Because there's something more here than just conditional independence, right? So there is causality. And if you have situations like this, right, what you need is to do causal inference, right? So causal inference means you're really testing if one variable causes the other, right? One variable is the cause, the other has the effect. So typically we call it causes and treatments. Treatment and diseases, right? So in medical scenarios, you want to look at, is this drug really, responsible for a certain effect, right? So those are the different, causes, and now you're looking at what is the effect this drug is having, and which one can you attribute it to. And same with symptoms and diseases, right? So with symptoms, there are symptoms you have and there are underlying diseases, right? Which diseases are causing those symptoms, right? Not the other way, right? The diseases cause symptoms, right? Not the other way. So that's the cause and effect model, right? So like this form I wrote down, generally this is called linear structural equation modeling, SEM, and in econometrics that's the terminology used. So I can write down a bunch of equations of which variables generate others, right? So in this example here, simply my variable at time t is generated by the variable at t minus 1 and some noise variable, right? So here in this case the graph would look like this, right? So in yt I have like yt minus 1. So this is directed now, and there's also some noise variable, right? I also, let's say zt. So this is my graph now, which is different from the Markov graph I earlier showed, because now I have directions. Right, so this is strictly more information than that undirected graph. Right? And so very quickly what I want to talk about, how do you come up with causal inference, right? Because now I want to ask, even just let's say, I'll take just two variables. Let's say variable I causes variable j. So how do I estimate the strength of how much is the variable I causing variable j, right? That's the inference problem. I want to look at the strength of that, right? And for a general distribution, this is hard, right? Because testing for causality is hard. And so people make these linear assumptions that yj is, right, similar to the model I had there, yi plus some noise. So if I make linearity assumption, then I have hope of computing this, right? Because now I can look at what is the impact of variable I over variable j. I can fit this linear regression model, right? And I can compute A. So I have to make some more assumptions for causal inference, because for a general distribution, this is very hard to compute. And what would make it right, so if this is my model, I can just do linear regression and I'm done, right? That's it, like I don't need anything more. But what makes it challenging in practice is, first of all, this is usually never happens in practice, right? This is too simplistic. And even if I make linearity assumption, most of the time, there isn't just the variable I and j, right? There are so many, all these other variables too, right? And they could like have you confuse, right, what variable I is doing to variable j. And so typically what we have is these confounders, and in that case, right, so I have now I and j, now I have another variable k. What if it has an effect both on I and j, right? So we call that a confounder. You can easily confuse this variable effect for I causing j. Because if I marginalize out k, right, there is no way for me to know what is happening between I and j. Right, it's ill-post. If all I have is marginal distribution of I and j, I can never tell you anything about the confounder. Right? And that's why interventions are critical to do causal inference. So when you have interventions, right, what you're doing is explicitly intervening and changing the distribution of one variable and looking at what is the impact on the other variable, right? So like in this example here, what an intervention means is I go and I fix the value, right? So instead of, if I just looked at the joint distribution of this, right, for instance, let's say they're all Gaussian, I can start with a Gaussian, I can then generate the other, right? But instead, I'll just say that let me set yi to be equal to 0. Right? So here now I'm intervening, and now I'm looking at what happens to the other variable. Right? And similarly, I could set, in a different setting, I could set yj to be equal to 0. Right? So here what these are doing is it's changing the distribution. It's no longer the original distribution. Right? Whereas in all the things we discussed before, there's just one distribution and I'm estimating that. Whereas causal inference fundamentally differs from that because I'm going and intervening and changing my distribution. And a simple way to intervene, what people usually do is set some variable to 0. Right? I mean, the example is, right, your hypothesis is smoking causes cancer. Right? So how did people go about testing this? You know, they had, like, of course, different covariates, right, different demographics of people, but they also controlled, right? They had, like, some population that had given up smoking, like, you know, they controlled and they said, right, this population now won't smoke, right? So that's like setting, say, the variable to 0. So you're changing the conditions there, right? So it's no longer the same distribution as before. And that's why it's called an intervention. Right? I mean, another simple example is, let's say, like, you know, there is you have this artificial lights to grow plants, right? So you can easily determine the cause and the effect because if you switch off the light, then the plant dies, right? That's no longer the same distribution because you went and changed the conditions that were there from before, and that's why that's called an intervention. Because a lot of people have confusion between intervention and conditioning, right? This is not equivalent to conditioning. Because in conditioning, I've still fixed my original distribution, right? And I just look at what are the values, right? I only look at the subset of values depending on that condition, and I look at the distribution. Whereas in intervention, I went and changed the distribution.
This means we just delete that h between ing. We do the integration.
Right, in the causal graph, right? Not in the undirected graph. That's the difference. So if you're doing intervention on a variable, you can delete that node in that, right, causal graph. And so what it will have an impact is only on the downstream, right? Whoever are its children, you see the effect of the intervention. Of course, if there's a parent of it, then there is no effect, right? If you intervene here, this has no effect. And that's how you can determine the directionality through interventions. Right?
Yeah. And also if I want to focus on the influence of I to j, but there is many other unobserved variables, so how can I fix all of it?
Right, you cannot intervene on what you don't observe, right? Yeah. That's why that's a challenging problem. You know, we have a paper on that, so at some point when we have that ready, we'll share that. But it's a highly non-trivial problem. So you have to make certain modeling assumptions. You have to assume you can intervene on your observed data, right? And what does that tell you about the hidden data? Yeah, but that's why that is extremely difficult, right? So, because I guess you see a lot of discussion, right, on Twitter and elsewhere that yes, we need causal inference, but what's stopping us? What's stopping us is the inability to do interventions, right, in most practical settings. Unless you're Facebook or Google and you can go do all these A/B tests and do this, right? You can do interventions there, but then the challenge there, it ends up being complexity, right? Because I can't do simple linearity assumptions. And even there, I can't take care of all the unobservables, right? I still don't know everything about the users. I still don't know what conditions led them to click on an ad or what things, right, determine the outcome. I can't have information about all of it. And that's why, you know, I brought this up because in the previous classes we talked about latent variable models, right? We talked about using tensor decompositions for that, And so the next interesting question is, can you combine that with interventional data and do both, right? Like discover latent variables, also determine what are the causal effects. So that's an exciting direction to combine those two.
Yeah, as to something to understand. So you wanted to understand if I, for example, causes J.
Yeah.
So what you're doing is this. You once remove I, go and check whatever you get, your parameter estimation, regression, whatever you have, over all other variables. You look at this thing that you learned from that, and you also do it with UI, right? And then you compare these two models.
Right, exactly. That's called the observational model, right? Where there are no interventions, that's called just observational model. So that's the baseline, right? You always start with observational data. And now you do interventions, you compare the two.
It's kind of the hypothesis testing that you said, and then you probably say this one or this one, right?
Right. I mean, you can, again, depending on which hypothesis testing can be used to decide what interventions to do, right? Because if you have lots of variables, you have limited subjects, limited samples, right? You cannot do all kinds of interventions. And that's why drug trials, right, take that long and take that much of approval and all those processes, right? Because the question is, what would determine this to be an authentic effect of the drug, right? How do I select my subjects, right? How do I make sure I record everything about them? What kind of measurements should I have, right? So that's where it's the most developed, right, for that area.
So for example, do we know now at this point that, for example, smoking is causing cancer, something as small, because do we know exactly, for example? But I mean, at the end, it gives you some probability or something. How do you know that for sure it causes or not?
I mean, that's overall a policy decision, right? If, say, some model tells me that, again, assuming it's a calibrated model, that with 90% confidence, I think this is a real effect, then, it's a policy decision. What do you do with that, right? But the other aspect, of course, is, right, there's so many other studies, right? So one, this is like causal modeling, but then there would be other mechanisms. So people go, they do it, they look at tissues, they look at the effect, they look at pathways, right? So it would be combination of all this. Usually it's never in isolation, right? And that's why drug studies require all these, like, explanations of what are the pathways, right? People need to go in stages. They need to show in tissue it works, right? In mice it works. So you need all that with the hope that way you can get like a true effect and not something spurious. Okay, but this is challenging, right? But the hope is, as we get more data in all domains, including biological domains, the hope is we can do more sophisticated causal inference. Because there's no free lunch, right? If I don't have good interventions, good quality data, lots of data for high dimensional modeling, there is no way around it, right? The other aspect is, of course, the more I know about the domain, the more I know about the mechanisms of how the drugs interact with various, right, conditions, then I could also use that. And that intimately connects with the statistical inference we discussed in the first part, right? Because you can talk about Neiman-Pearson tests, like, I want to make sure I don't make spurious discoveries, or if the drug has an adverse effect, that is bad, right? So I don't want to miss detecting that, but I don't want to have false alarms, right? So all those aspects also tie in very much. When I want to truly make sure that this is a causal effect and this is not something spurious because of a confoundum. Right? And that's most critical when we have, right, things to do with human body and human lives. Okay, so very different set of considerations from other things we look at when it comes to machine learning applications. Any questions here? Okay, so in the last remaining time, I want to talk a bit more about learning, and in particular, learning this graph. right? Because as I said, once the graph is learned, the rest of it is easy, right? So how do we learn the graph? When can we learn the graph, right? That's a challenging problem. Oh, before I do that, I wanted to quickly kind of make a comment, because I think in the recitation, you looked at tensor diagrams, right? Or tensor networks, tensor diagrams. Do you recall what that is? How many of you attended that recitation? Okay, so but I think anyway the slides were made available and it's quite simple. Right, so just to recall, right, we had this tensor diagram where the nodes were tensors, right? And the edges were like, the outgoing edges were telling me the order of the tensor. And if I joined two tensors along an edge, that means it was a contraction. You recall that? Right, so this was a tensor diagram where, right, this was just a matrix, right? So I represented my matrix just this way. I mean, there's no contraction here, but because there's just outgoing edges. And similarly, with the third order tensor, we did this. Right, so I have this representation, and now I'm talking about graphical model, and I'm talking about the representation here, right, factorization here. So the question is, how are the two related? Right, I mean, so far this appears to be no relationship, right, because just kind of from ground up talked about how when I have the graph, I can factorize my distribution in terms of cliques of the graph. So, can I express this in terms of tensor diagrams? And so for this, the main intuition is, for simplicity, I'll just look at two variables, right? So let's look at graphical model. I just have two variables, say I and j, right? So trivial, right? So in this case, I can just write down my joint distribution, right? So this is just p of yi, yj. If I want to represent this as a tensor diagram, what would I do? I mean, all discrete, right? We're only dealing with discrete distributions. Because this is a matrix, right? So my joint distribution is a matrix, right? Because I can write down all my configurations on the first variable and the second variable. So if I wanted to look at my tensor diagram for representing this joint distribution, I would write it this way, right? Because that's how I represent a matrix, right? Because here this was my matrix, right? P, let's say P is my joint distribution matrix. Here I and G. How are these two graphs related? Can somebody recognize the relationship? Does something jump out? How many nodes are in the first graph? 2, right? How many nodes are in the second? 1. How many edges are in the first? 1. How many edges are in the second? So what do you think is the relationship? How can I transform this graph to get this? Is there a simple transformation? What do you think? Yeah, switch edges and nodes, right? So this is a duality transformation. That's called a dual graph. So if you recall, like incidence matrix, right? So if you have the incidence matrix of a graph, right, there are nodes and edges. Let's say this incidence matrix is M. For the dual graph, the incidence matrix will be M transpose, right? So I just switch my nodes and edges. So in my graphical model representations, I'm putting the nodes to be the variables, right, and the edges as the factors. Whereas when I write the tensor diagram, the factors are always the nodes, right? So that's why I just switch the representation. So whenever I have the Markov graph, all I need to do is to do the dual graph and I get a tensor diagram. And if I do contraction on the tensor diagram, that's equivalent to computing marginals of that distribution. Because if you recall the marginal, right, so if I, let's say, simply I want marginal of a node, what I want to do is look at my joint distribution, right, and but not include I, right, minus I. Let me just put it this way. So I sum up on everything else except that variable. That's marginalization, right? Right, marginalization just means I sum up on all the other variables except this one. And the way we do in the graphical model is, let's say I have this factorized form, I can try to use that factorized form, right, to do the marginalization. I can do the same in my tensor network by doing contraction, right, because, so let me do an example, I think it'll be easier. So let's say for marginalization, this is my graphical model. So here JK, right? So if I want to marginalize on this, I want to sum over these two variables. If I now look at the dual graph, so what would the dual graph look like? I need to represent a node for this edge here, right? So now there is a node ij. There's another node jk. So what should I do? Right, I mean ij and jk are connected through j, right? And this is I, this is k. This is my dual graph. Right, so if you think for a minute, you can see one is dual of the other. Right, and with this tensor diagram, I can now do the relevant contractions, right? For instance, what this tells me is if I want my marginal distribution on I just need to contract along this, right, tensor network. So I can decide how to do the contraction along the tensor network, and that gives me marginalization. Okay, so that's the connection between what you looked at in the previous class with tensors and graphical models. Right, there's a different connection. Because now I can relate my graphical model to the tensor diagram, and I can relate marginalizing my distribution to contracting over the tensor diagram. Any questions here? Is that example clear?
So you end up with some sort of, because now you have two edges sticking out of the tensor diagram. Does that represent
that represents the order, right, of the tensor, if you recall, the edges stick.
So do you have now a matrix with the probability of I, the joint probability of I and K?
Right, so once you contract over J, right, so that would be the equivalent, if you want to contract over J, then what remains is the joint probability of I and K. So you can do that marginalization by contraction. So by contracting on relevant edges, you can marginalize the variables. Because there is a variable connecting, right, these factors. So if you contract along that edge, you marginalize that variable. So in this example, the J is the common variable, right? It's the one connecting these two nodes. And so by doing that contraction, you're marginalizing. And that's why you can compute marginals by contracting along the tensor diagram. So you decide what to contract depending on what marginalization you want. So it's convenient, right? I mean, you can directly do it by writing out the summation, but the tensor diagram just makes it convenient. Because that's another nice connection, right? Because, you know, when you looked at tensor diagrams, we argued it's a nice way to represent different contraction operations on tensors, right? So it gives a convenient way to write down complex distributions and compute their factorizations. And the packages that do that well. So because then underneath you can ask, can I make tensor contractions more efficient? Can I parallelize them better on CPUs and GPUs, right? So if I can speed up tensor contractions, I can also speed up computing marginals in my graphical models.
Can you use something like the kernel trick for these tensors?
So the kernels, so far we only looked at discrete distributions for that reason, right? If you want to now extend this to non-parametric continuous distributions, a standard formulation is to kind of have kernels to represent these pairs and marginals, right? So you can like kind of make these distributions non-parametric. So if it's a acyclic graph, that's immediate, right? Because you can directly relate to marginals. For the general distributions, it's more challenging because you could put the kernel here, right? You could say this is like I can, represent this in some Hilbert space, right? But then the normalization is still hard. If you can get away with not doing normalization, that's okay. And that's where like belief propagation and those algorithms just do approximation, right? There's no guarantee they would compute the exact marginals or exact normalization, but they approximate. So the kernel trick is orthogonal to this, right? If you want to represent non-parametric continuous distributions, you'd have to, that's one approach, right? You could like design kernels and then the kernels are on a graph and there's still the factorization form. I mean, you can also combine this with deep learning, right? Which we've done in a few papers where the idea is the kernels could be derived through the features, right, in some intermediate layer. And then on that layer, you still learn a graphical model. I mean, one of the good applications for this is if there are hidden variables that haven't been labeled, right? So even in standard computer vision, you can label like certain things in the image, but many things are not labeled, right? And this is the problem of lack of enough specification, because let's say, in standard ImageNet, there's just cat and that's it, right? But real world images are not just cat, there's all kinds of things around the cat. And so many things get, missed. And you also miss labels of the bigger picture, right? So for instance, a picture of this room, I can say, okay, human, right? I could have the annotator label that, but the meta label is, this is a classroom. Right, so how do you discover those kind of hidden variables? How do you look at relationship between variables? You can do this in combination with deep learning if you now design kernels based on features derived from some deep network, right? That gives a representation. On top of it, you can also aim to learn the graphical model. Yeah, so there are interesting ways to go beyond. But most of the class I limited to discrete because, right, to have the definitions and to kind of explain the concepts, it's much cleaner. It's a good point. Any others? Good, so in the next class we'll deal with structure estimation. I know I realized I wanted to do this tensor diagram because I think it very nicely connects with the previous one. We'll also touch upon competitive optimization, so we'll try to do both. But I do want to cover the structure estimation. Thank you.